SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome to the next lecture in interfacial fluid mechanics. In today's lecture, we'll be looking at the effect of surface tension. This is a direct extension of what was done in the last lecture where we looked at the molecular origins of surface tension. The goal of today's lecture is to get you some intuition, build some intuition in all of you on what surface tension does to various problems. To keep matters simple, I'll be looking at examples from capillary statics. Now, one of the things that all of you must have heard about surface tension is that surface tension minimizes surface area. This is a consequence of what we saw in the last lecture, which is the surface tension or interfacial tension is directly connected to the free energy of an interface. And therefore, if you want to minimize the free energy, then we minimize the surface area. This is normally looked at using figures like this or examples like this. So what you see on the left here, which I will label as 1, okay, what you see is a cube. It could be any other geometric shape, and if you were to let it evolve and experience in the presence of surface tension, that where surface tension is basically acts on all the faces of this cube, then you would basically get a sphere. A sphere because for the same volume, the sphere has the lowest amount of surface area. The same thing would happen if the same cube were to be placed on a substrate. But here there are additional constraints. In addition to minimization of surface area, we also have to adhere to the boundary conditions at the surface. And therefore, the sphere would evolve to a dome shape as you see here. If the droplet or the liquid is of very small volume, then you go from a cube on a surface to something like a hemisphere on a surface. Okay, these are the two examples that we see. Okay, now we can also do some experiments, and we will see some of these later in the course. For example, here I'm showing you two illustrations here. So the first figure, what you see is a wire frame that is shown in black. So I'll call this as the wire frame. Okay, you can basically take any wire frame, basically make it into some kind of a rectangle. Another way to make this is take the OHP sheet that you get, a transparent sheet, plastic sheet, cut a rectangle in it. Now you dip this into soap water, and what you get is a soap film. So this, what you're seeing here, the shaded region, is a soap film. I'll make a drawing of what the soap film actually looks like. This is a soap film, and on the soap film we have put a thin, very thin rod. Okay, its mass is very small, and we're puncturing the soap film on the right side of this rod. Now there is a soap film on both sides of this rod. This rod is basically touching the soap film. The moment you basically puncture the soap film on the right, what happens to the rod is the rod moves to the left. Okay, now I've shown this, the direction of motion is shown with an arrow. Okay, this is basically, it's experiencing a force because of surface tension gamma. So we can actually write down what is the work done. We can write down work done, let's call it as delta W. This will be force times dx. Okay, where if the rod was initially at this position and has moved by a distance dx, then the work done would be force times dx, and this force here would be 2 times surface tension times the length of the rod times dx, where this is L. Okay, and why do we have 2? To understand why we have 2, we have to look at the soap film itself. I'll make a simple drawing of the soap film. So the soap film here that you see here is, you have air above, we have air above, and we have air below. Okay, so, or maybe I should do it in 2D, in 2 dimensions. The soap film would look something like this. Okay, we have air above and we have air below, and in the middle, what you have in this region, what you have is soap water. This appears like a thin film because typically the thickness of this film is only a few microns, but we are talking about an experiment which is spanning several centimeters. Okay, so for all practical purposes, this is the 2-dimensional film. Now we can actually zoom into this region and ask, how does a soap film actually look like? Let's say I zoom into this region here and ask, how does it look like? Okay, so here's my zoomed version of the soap film. You have, or let's say I zoom into the upper region. I zoom into this part of the soap film and I ask, how does it look like? Okay, so what we have now is we have water at the bottom, or soap water at the bottom to be precise. Okay, and we have air at the top, so we have air and soap water. And now if you actually were to dip this wireframe or any rectangular cutout in a large OHP sheet or a plastic sheet, you just dip it into water and pull it out, you will see that there is no thin film that is formed. Okay, even if it forms, it'll last only for a few milliseconds or a few seconds. You can't really do any experiment with it. So one of the ways to create this thin film is a soap film, meaning you do it with soap water. And the reason we do this with soap water is because we have these special kinds of molecules called surfactants in soap water. These molecules, basically, if I were to show how these molecules look like, so here's basically, I can think of an interface. One side is, let's say, water, and the other side is air. Okay, these molecules typically have a dual nature. Okay, so it's a long chain molecule where one side of the molecule, it has a head which likes water and a tail which does not like water. So if these are not charged, you can call them as non-ionic surfactants. Okay, we're looking at surfactants. Okay, these also come in other varieties. For example, you could have an anionic surfactant where you have a negative charge and a tail which does not like water. So this is hydrophobic part and a hydrophilic part. You can have, this is an anionic surfactant. Okay, we can have cationic surfactants. And finally, you can even have surfactants which have both the groups on their head. Okay, we can show them as two separate heads, a positive and a negative. So we have anionic, we have cationic, and this is an amphoteric surfactant. So surfactants come in all kinds. If you have charges on them, you can even subject them to electric fields, and they would the interface stresses would be different on the surface. Okay, so now if I were to use these surfactants and ask what is happening to these surfactants on the surface, we see that there is a head which likes water and a tail which does not like water. The moment you basically take soap water, meaning add soap into water, what really immediately happens is these molecules, which basically at the part of the molecule which does not like water, sticks itself out. So you have a tail and you have a head, the heads basically stay inside water, but the tail, which does not like water, basically sticks itself out. So this part is hydrophil, and this is hydrophobe. Okay, these molecules are essentially crucial to stabilize this thin film. Otherwise, the soap film would just rupture. Okay, very, very easily. Now, there are other consequences also of the soap film, of this surface tension. One of the other common consequences is a meniscus. Okay, we've already seen this earlier. So when you basically dip a tube or even a plate into water or any other liquid, you will see that there is a small meniscus that is created. So by meniscus, what I'm referring to is this region here. So if I were to examine this region more closely, what you really have is, this is basically the surface of either the tube or the plate, shown in black. And what you see in blue is basically the interface. And you could even have any angle depending on the nature of the surface. So this angle is the contact angle. Now in this particular case, it's just static, so we can also, nothing is moving, so we can even call it the static contact angle. And you have an interface where the interface bends, but far away the interface has to return to its horizontal state because gravity is basically pulling the fluid down. So there is a competition that's happening between gravity and surface tension, and a natural length scale emerges. We will look at what is the length scale, what is the typical value of this length scale for, let's say, an air water system, is something that we will be looking at more closely. Another thing that we'll also be doing in the course is to determine the shape of this meniscus. So this is a meniscus. Okay, and this angle that you see here directly influences the shape very close to the solid surface. Okay, another common experience is basically the case of a droplet. What you're seeing here is a droplet that is sitting on the surface. Now, instead of looking at it as a three-dimensional image, let's look at it as a two-dimensional image, where we are looking at the cross-section of this droplet drawn right at the middle of the droplet. Now, I'm showing you two images here. In the left image, what you have is an angle as measured inside the liquid. This angle as measured inside the liquid, this angle is greater than 90 degrees. Okay, and so this surface is referred to as a hydrophobic surface. One way to understand why we call it a hydrophobic surface, hydro refers to water and phobic comes from the word phobia. Basically, it means it does not like. Okay, so this is a surface which does not like the liquid, or in this case, typically water. Okay, why do we say it's hydrophobic? Now you can see mechanistically, if you can see this angle, the angle is greater than 90. So if you take the same volume, what is really happening is the amount of the area that is in contact with the solid is reduced if the surface is hydrophobic. On the other hand, if the surface is hydrophilic, where theta is less than 90, and here the angle theta is basically the angle as measured inside the droplet. So this is, again, there are several ways to measure this angle. So typically it's a tangent to the surface of the droplet to the tangent to the plate, and it's by convention it's usually measured inside the droplet, liquid droplet. So if the angle is less than 90, what is really happening is the drop likes to spread itself out. It's maximizing the amount of area the drop is in contact with the solid. In this case, the solid is referred to as a hydrophilic surface. Now the word hydro is used with water because this is the most common fluid that is used in many experiments. But for specialized experiments, we could use oils because of their viscosity and surface tension. So if you're using oil, then the word essentially is The same ideas carry over to oils, but instead of calling it hydrophobic and hydrophilic, we would be calling it as oleophobic and oleophilic. But the ideas remain the same. Okay. So we've looked at we saw that surface tension. One of the things that it does is when it interacts, if it was in free air or in where there is no solid surface, then surface tension would try to minimize the surface area. But when it is in contact with the solid, then there is another interaction with the solid that comes in, and you'll have new vocabulary that has entered our discussion, which is words like hydrophobic and hydrophilic. Okay. Another vocabulary that is very important when we discuss surface tension is the so-called Laplace pressure. Okay. This is something that we will be discussing now. Okay. To understand the notion of what is Laplace pressure, let's start with an example of a balloon. What I'm showing you is a nice, beautiful red balloon. Now, as you can clearly see, the balloon is actually tied at the bottom, and the reason you need to tie it at the bottom is to ensure that the air is inside the balloon is not escaping. Why would the air inside the balloon escape? Because if you look at the forces that this balloon is experiencing, it's experiencing a pressure from the outside, which is the atmospheric pressure. It's also experiencing a higher pressure inside. So the pressure inside the balloon, you can now say P inside. If the P inside is higher than P outside, only then the membrane of the balloon would be in a stretched state. So what is balancing the pressure inside? What is the force balance? What is really happening is that the pressure inside is always constantly trying to push the balloon out, but the elasticity of the membrane coupled with the external atmospheric pressure is actually able to hold the membrane balloon together, right? If the elasticity of the membrane is unable to hold it, the balloon would burst, right? And as soon as the balloon bursts, immediately what you have is that the air inside the balloon, because it is at a higher pressure than outside, it would escape. Now the same idea can carry forward to a bubble or a drop, and that's where we have the notion of the Laplace pressure. Now let's consider the case of a two-fluid system. I'll show the case of a droplet. It could be any two fluids. So let's start with, let's say the fluid inside is A and the fluid outside is B. Okay. This could be, if it's a liquid droplet in air, then A would be the droplet liquid and B would be the atmosphere. But if it's a bubble, then A would be the air and B would be the liquid. Now let's look at the case of a bubble like this or a droplet like this, two fluid system like this. Okay, we want to do a quasi-static experiment. I call it an experiment, but it's not really an experiment, it's a thought experiment. Okay, now we'll start with a bubble or a drop of radius r. What I now want to do is, I want to stretch this radius to a new radius this extension is dr. So therefore now what I have is the new radius that I have stretched to is r plus dr. I've stretched it to a new radius r plus dr. Okay. So the pressure inside is PA and the pressure outside is PB. Okay. So this is a quasi-static experiment. There is no motion, or if there is motion, it's so slow that viscosity has no role to play. Okay. The question that we are interested in asking is, what is the pressure? What is the relationship between the pressure inside and the pressure outside? Okay. So, the question that we are asking is, what is the relationship between PA and PB. Okay, just to quickly recap your memory, in the last when we derived the jump conditions, we said if there was no surface tension, then the pressure across the interface is the same. There is no jump in the pressure. So therefore, if there was no surface tension, then the PA would be equal to PB, right? But now we want to impose a surface tension. So let's call the surface tension as gamma. And we want to ask what is basically the relationship between PA and PB in the presence of surface tension gamma. Okay. Now, so how do we address this problem? We start by basically writing down the expression for the work done by pressure and any capillary force. The work done by the pressure and capillary force to change the radius from R to R plus dr. Let's write down what is this work done. Okay, this work done, well, I'll write it as delta W. This quantity is equal to minus PA dVA, because you are actually increasing the volume, okay, of changing the volume of A. You are also consequently changing the volume of B. And then there is a capillary work. There's a force because of capillary forces, which you can call it as gamma AB times the change in the area. Remember, we've seen that there is the work done would be equal to the change in the free energy, and this would be directly related to surface tension times the change in the area. Okay, so this is basically my expression for the work done or mechanical work done. Now we can write down expressions for each of them. Okay, so what is the expression for dVA? Okay, the change in the volume of this would just be 4 pi it's actually technically approximately 4 pi r square dr. Okay, here what are we assuming here? We are assuming that dr is much smaller than r. Okay, similarly dVB would be exactly the same but with a minus sign. If I, as shown in the figure, A is increasing and the volume of B is decreasing, therefore there's a minus sign. And I can similarly write down the change in the area. Exactly, it would be 4 pi r square or 4 pi r plus dr, that's the final area, minus the initial area. And if I ignore dr square terms, then what I have is I have 8 pi r dr, right? Now, having calculated all this, we can now substitute this into the work. So I have minus PA times 4 pi r square dr. Then I have minus PB with a negative sign now, 4 pi r square dr. And finally I have gamma AB times 8 pi r dr. So that's the expression for the work done. And we will simplify this in the form. We can combine a few terms here. 4 pi r square dr is common. PB has a positive sign, so we have to take that into account. We have minus of PA minus PB times 4 pi r square dr, and I have plus gamma AB times 8 pi r dr. That's the simplification that has happened. Okay. Straight away now I can write down what is the condition for mechanical equilibrium. for mechanical equilibrium, these two effects, meaning the work done by the pressure and the capillary forces, are perfectly in balance, and therefore I have dW would be 0, and this immediately leads me to a nice simple expression, minus of PA minus PB 4 pi r square will I can dr, let me write it most step by step, 8 pi r dr would be 0. Okay, dr is clearly non-zero. Okay, or rather I want to find out for all possible values of dr what will be the result. What I now have is a simple relation between the pressures. PA minus PB would be gamma AB times 2 by R. Okay, this is a nice, simple, elegant expression that we have got here. It says that if gamma AB, so there are several things that we learn here. The first thing is if gamma AB is not equal to 0, then PA is not equal to PB. As long as we are referring to a case where R is not infinite. Okay, R, we will also look at those cases. The second observation is if gamma AB is not equal to 0, R is finite, then PA is greater than PB. And more specifically, I can write PA is PB plus 2 gamma AB by R. Okay. So this can also be written verbally as the pressure inside the drop or bubble is greater than pressure outside. Okay, so for all practical purposes, a droplet or a bubble is exactly like a balloon that I've shown here. Okay, now we can actually even examine it for the case of a soap bubble, and this is something I showed a video in the introductory lecture. If I take a soap bubble, I'll make a very quick drawing of a soap bubble here. What you have in a soap bubble is you have two surfaces. Excuse my drawing, but this is clearly, I'm showing that the thickness is quite exaggerated. But what you have in a soap bubble, you have air inside, air outside, and you have soap water. This is a soap bubble in the air, and this is commonly made by little children. It's amusing to children. One of the most amusing things to children is that these soap bubbles, they pop. Why do they pop? They pop because the pressure inside, let's call it as A and B, okay, the pressure inside is higher than pressure outside. To examine this, let's say that the thickness of the bubble is negligible. Okay, so the thickness of the bubble is negligible. What you really have is, if I were to look at a close-up view of the bubble, let's say I'm looking at a region here. Okay, so you have, if the thickness is, let's say, T, and the radius of the bubble is R. Okay, now we have two surfaces here. We have a gamma and a gamma. Okay, so we have air here, and you have let's say, I'll just say water. It's soap water, and you can even label them here. We'll call this as A, we'll call this region as B, and we'll call this region as C. Okay, let's first look at the region C. Okay, now using this expression, PC is equal to PB plus 2 gamma AB, sorry, 2 gamma BC divided by the radius. Radius would be r plus t. But if you say that t is very, very small compared to r, then PC is approximately PB plus 2 gamma by r. I have removed the subscript BC because this is just surface tension gamma, and it's the same whether you're looking at an interface between fluids B and C or between fluids A and C. Okay. Similarly, we also have pressure inside C, pressure inside A, sorry, is now equal to PC plus 2 gamma by R, right? Because there is again a curvature, so the pressure inside. So we're looking at 3 points across the interface. So we're looking at the pressure jump across these 2 points, that is PA is equal to PC plus 2 gamma by R. And similarly, we're looking at the relationship between these 2 points here outside between B and C interfaces. PC would be PB plus 2 gamma by R. And now if I were to combine both these relations, what I have now is pressure inside PA. I substitute for the PB. What do I get is the pressure outside the bubble plus 4 gamma by R. Okay. Or this is nothing but PB plus 2 times 2 gamma by R. Okay. Why do we get this extra factor 2? Extra factor 2 is because we have 2 interfaces. Okay. So having looked at the pressure across an interface, a curved interface, now we can sort of make a general statement. The general statement would be as follows. If, or rather, for a curved interface, with surface tension, delta P is not equal to 0, where delta P is the jump across the interface, is not equal to 0. This delta P, the jump, non-zero jump across the interface, is often referred to as the Laplace pressure jump. Okay, it's a direct consequence of 2 effects. One is surface tension and the other is curvature. Okay, now let's look at we have looked at 2 consequences here of this expression. PA minus PB is 2 gamma AB by R. So we've looked at cases where gamma AB is not equal to 0. Okay, and we found that there is a jump across the interface. Let's look at a third consequence. The third consequence is, for a flat interface, even with gamma AB not equal to 0, okay, for a flat interface, PA is equal to PB. Why do we have that? Because if you look at it here, so basically a flat interface, okay, the curvature of this flat interface, curvature, or the other radius of curvature, goes to infinity, and therefore this term 2 gamma by R goes to 0. So for a flat interface, the pressure jump across the interface, PA, is equal to PB if the interface is flat. Okay, so it's a combination of 2 things, surface tension and curvature. Okay, we'll look at curvature more closely, but before that I want to talk about what is the effect of gravity in this discussion. So here, Lizzie, notice that I'm only talking about pressure jump across an interface. So even though I show 2 points on either side of the fluid, we have to assume that these 2 points are very, very close to each other and just across the interface. So there is no appreciable change in the vertical height. Let's say if there's vertical as in when there is gravity. So there is hardly any variation in hydrostatic pressure or variation because effect of gravity in this particular statement is negligible. So the statement that is shown in the box here ignores gravity because you're looking at cases where just across an interface. Okay. Now let's look at the case where there is gravity and how does this contrast with, let's say, in the presence of gravity. Let's do a simple thought experiment. Okay. The thought experiment is as follows. Let's say I have a large vertical tank. Okay. You could think of it as a reservoir here, and this reservoir has an interface here at the very top. Okay, and it's flat there at the very top. Above that is my P atmospheric pressure. Okay, we'll call this as location, the surface, as z equal to 0. Okay, let's look at what is the variation at 4 different locations. Let's first look at the first location that I'm interested in is, let's call it as Z1, where Z1 is very, very close to the interface. Okay, so we'll just think of this as a water tank and we have air above. Okay, and Z for me is positive downwards. Okay, now let's look at a case where I have somewhere in the middle. We'll call this location as Z2. Okay, or position 2. This is position 1. Okay, and finally I can have a case where I'm at the bottom of the tank, Z3. Okay, now let's look at the variation in the pressure, the pressure inside the droplet because or a bubble at these 3 locations. Okay, so I'm interested in asking what is the pressure inside a tiny bubble at these 3 locations. Okay, in each case we will take the bubble to be of radius r, and so the radius of the bubble is r. So let's start by asking at z equals z1. Okay, so we can now say since water level is flat, okay, so we have air inside the bubble as well. We have air in the atmosphere. So if the water level is flat, I can now say that the pressure at the first location, the pressure of the air at z equal to z1. So here for me, so this is A, okay, and this is P outside at z1. This will be 2 gamma by r, where gamma is basically there's air inside and outside. Okay, and clearly outside the pressure is basically atmospheric pressure plus rho g z1. Okay, that will be P atmosphere plus rho, and we have to be careful about what is this rho of the water g z1. This will be equal to 2 gamma by r. Okay, that's the first case, and I can now say that pressure at z1 is approximately P atmosphere plus 2 gamma by r, because I'm saying that z1 is very, very small. Okay, it's very small. Now let's look at z2. Okay, at z is equal to z2, the pressure inside the bubble at z2 will be equal to the pressure outside the bubble at z2 plus again 2 gamma by r. Okay, so this is air inside and I have outside the bubble, and the pressure of the air outside would be P atmosphere plus rho water G Z2, that's what I have, plus 2 gamma by R. Okay, so I have P atmosphere plus 2 gamma by R. This is basically because of the surface tension effects and then atmospheric pressure. But then because the outside itself, the outside fluid at location 2 is experiencing the weight of all the fluid of weight of water up between 2 and 1, I have this additional pressure. This is the hydrostatic pressure, rho GZ2. So now you can actually say this part is atmospheric pressure, and this is hydrostatic pressure. And this little region here is because of extra pressure inside the bubble due to surface tension. Okay, so the pressure inside the bubble is over and above the value of the surrounding pressure, outside pressure. Okay, so I use the word curvature a few times. Let's look at what is this curvature. Okay, so let's start with the case of a circle. If I want to take a circle, okay, or maybe I could just draw an actual circle. Okay, this is a circle. The radius of the circle is R. If I say the radius of the circle is R, then I straightaway have I can say that the curvature of the circle, the curvature, it tells you how quickly does the normal vector, how rapidly is the normal vector turning as I go around the circle, how this normal vector, how quickly is this normal vector turning. Okay, this curvature in this case is 1 by R. Okay, now let's extend the same idea to a sphere. If I have a sphere, then I have two circles that I can draw at any given point, which are orthogonal to each other. If you think about the case of the Earth, okay, I can draw a latitude and a longitude. Let's say you're on the equator, then you have a latitude, that is a 0-degree latitude, and you also have the longitude going from the pole, North Pole to the South Pole. So you actually have two circles. I'm ignoring small effects here, like saying that the Earth is strictly not a sphere. But if you think of a ball, then you can draw two radii, okay, two circles, and each of those two circles have radii. If the radii for a sphere, you can actually say for a sphere, curvature is there are two radii and it's the average of the two. And because it's the average of the two, this is called the mean curvature. Okay, so for a sphere, the pressure inside, if you think of a spherical ball like this, where you say this is a sphere, this is going to be a drop or a bubble, and you say this is A and B. Okay, PA is equal to PB plus, the generalization of this would be surface tension. We saw 2 by R. Instead of 2 by R, the generalization would be 1 by R1 plus 1 by R2. Okay, since R1 is equal to R2 for a sphere, because everywhere the radius is the same, PA is equal to PB plus gamma times 2 by R. That's the 2 by R is the mean curvature. Okay. Now there are some surfaces, or there are many surfaces where the radius, the tangent radius that you're drawing at a surface to measure the curvature need not be on the same side of the surface. And I'll illustrate this with this very simple example. Now take the case of a pair that I'm showing here. Okay. Now at any point that I'm going to highlight in a minute, so let's say this point, we'll call this as point P. At this point P, I want to determine what is the curvature. Now clearly, I can draw two radii, two circles. There is an inner circle which of radius R1, and there is an outer circle of radius R2. Now clearly in this case, because there are two things here, R1 need not be equal to R2 in magnitude. That's the first point. The other more important point is that because these two curvatures, these two circles are on different sides of the surface, we also have different signs for the curvature value. Okay, so you can actually have surfaces where R1 and R2, or 1 by R1 and 1 by R2 are taken to be of opposite sign, and therefore they actually can even cancel out. Okay, and we will see surfaces like that when we discuss minimal surfaces. But one example that I can give you quickly is the so-called catenoid. So if you want to make a catenoid, the easiest way is take two rings rather. Take two circular metal rings, hold them apart at a certain distance, dip them into soap water and pull them out. Okay. As it turns out, the minimal surface is actually not a cylinder joining the top ring to the bottom ring, but it's actually this curved shape. Again, just like the example of the pair, we have two radius of curvature. So you can actually have one curvature like this. This is R1. And you have another curvature which is R2. In this particular case, 1 by R1 is exactly equal to minus 1 by R2. Implies the mean curvature. The conventionally the mean curvature is represented with the symbol H. The mean curvature will be 1 by R1 plus 1 by R2. In this case, it is 0. Okay. Now, we can easily see why that would be, we can physically explain why it would be 0, because this is a very thin film, okay, and it's a film that is going around, so it's open on both sides. So there is no soap film here, okay, at the top, no film here at the top and bottom. So clearly, if you go from a point here to a point here, both sides are exposed to the atmosphere, and it's atmospheric pressure on both sides. So the pressure on both sides should be equal to 0. So PA should be equal to PB, and therefore if I use the expression PA minus PB as gamma times curvature, or gamma times kappa, where kappa is also, that's another commonly used notation, kappa. So gamma times kappa. So if PA is equal to PB, then only option is then kappa has to be 0, because clearly surface tension is not 0. Okay. So we have seen in today's lecture various consequences of surface tension. Let me quickly recap what we saw. We started by looking at how surface tension minimizes the surface area. These are sort of the consequences of that minimization. This is a simple thought experiment. We'll see a video of this later, where you take a soap film and you see what is the force exerted on the rod. Okay, and from this we can estimate the work done, and we can actually say that this surface tension force is basically acting normal to the surface, normal to the rod. Okay, it's a force per unit length, and it's acting normal to the rod. And then we looked at very briefly, how what are soap films. Other consequences of surface tension is where you have an interface between two fluids meets a solid. Then you have this notion of so-called contact angle, and then We saw the new vocabulary enters our discussion, words like hydrophobic and hydrophilic surfaces. And then we looked at the notion of Laplace pressure. This is a very, very important result, where we find that if you have a curved surface and the curvature, net curvature is non-zero, and you have surface tension, then the pressure across the surface is always non-zero. Okay, so there is always, so if you think of a bubble or a droplet, then the pressure inside is always higher than pressure outside. Okay, if it's as long as the curvature is non-zero. We also contrasted how this pressure is different from hydrostatic pressure. Okay, and then we looked at some generalization of this curvature. The mean curvature in this case, kappa. Sorry, the mean curvature kappa will be 1 by r1 plus 1 by r2, where r1 and r2 in terms of magnitude can have opposite signs. So I meant the magnitudes can be opposite. Okay, so the net curvature can always be zero. Okay, can sometimes be zero. Okay, so finally let's look at some typical, so let's look at the units of surface tension. Okay, so let's call it as gamma. The unit of surface tension, this is basically force per unit length, and therefore this is Newton per meter. Okay, note that surface tension is also energy per unit area, and this would be joule per meter square. Okay, so if you work out the unit of Newton, the Newton would be kilogram meter per second square times 1 by meter, and therefore you would have kilogram per second square. Or in dimensions, you would write it as m power 1, L power 0, T power minus 2. Okay, so that's the unit of surface tension, dimension of surface tension. Now we will look at what about surface tension of some common liquids. For example, the two common liquids that I'll tell you is air, water. Surface tension is around 0.072 Newton per meter, and therefore this can also be written as 72 millinewton per meter. That's the value of surface tension. This is air, water. Okay, but whenever you have air, water, there's an important convention. So if the other fluid is air, okay, one simply refers to surface tension for a single fluid. Okay, note that surface tension it's a surface between two fluids. Okay, if the other fluid is air, then instead of referring to it as an interfacial tension, where it's an interface between two fluids, you call it a surface tension. So it's all right to say surface tension of water is 72 millinewton per meter. But strictly speaking, it's understood that the other fluid is air. Okay. Similarly, you can actually say surface tension of mercury is much larger. It's around 480, I think 486 millinewton per meter. Okay. Mercury has a much higher surface tension. You have various silicone oils whose values of surface tensions are around 20 to 30 millinewton per meter. Okay. So it's useful to know these numbers, especially the value of 72 millinewton per meter is something that we will use again and again when we do some calculations to estimate what are the typical length scales where surface tension becomes an important force. Okay. There's another thing that I also want to talk about a bit later in the course, which is what are the common ways in which surface tension is measured. Okay, but I hopefully found today's lecture interesting, and we'll then now look at jump conditions in the presence of surface tension. Thank you.